个因为这个 speaker 是我的指导教授，我以前博士班指导教授，所以我来介绍一下。就是他是从Johns Hopkins来的，那他的研究领域主要是调和分析。他今天讲的东西也跟调和分析有关系，但是他讲的问题也跟波方程很有关系。所以不管你是对这两方面有兴趣，也可以认真听一下。如果你有问题，等一下可以问你如果想不知道怎么用英文问的话，可以跟我讲我再帮你翻译没有关系。那接下来我们就欢迎那个Sogge教授。
Well, I'm not sure what he said, but I'd like to thank him for being a nice host, and I'd like to thank you all for coming and say that I'm happy to be in Taipei again. My second time. I was here back in July for a conference that was here.
But this is another city.
Yeah.
That's Taipei is called Hsinchu.
Oh, okay.
No problem. You get it later.
Well, you learned something. Okay, so let's get to this. So I want to talk about some work I've been doing over the last decade, most of it within the last couple of years, and it's joint work, as you can see, with a couple people. Matt Blair, who's at the University of New Mexico, and Steve Zeldich, who's at Northwestern. Both were colleagues of mine. Matt was a postdoc 10 years or so ago, and Steve Zeldich was a professor colleague of mine for a number of years, and then he left to move to Johns Hopkins, and since he's left, our collaboration's really taken off. It's much easier to work with him when he's 600 miles away. We've written 9 papers of our 10 after he left. Okay, so here's the setup. So I'll be talking about eigenfunctions. I'll be talking about eigenfunctions on compact Riemannian manifolds without boundary. So you can pose these questions when there's a boundary, but they become much harder. If there's a boundary, then you assume that the eigenfunctions satisfy either Dirichlet or Neumann boundary conditions, but I won't be talking about that. So you have a compact Riemannian manifold with a metric G of 2 or more dimensions. It's not interesting in 1 dimension because the manifold's a circle, really. And you consider eigenfunctions of the Laplacian, where the Laplacian is the natural Laplacian coming from the metric. So G lower jk are the coefficients of the metric. This is the inverse matrix. This is the determinant of the metric. And so you take this operator, which is self-adjoint with respect to the volume element. So this is the natural thing you learn about in Riemannian geometry. And the spectrum, I like to take the square root of the operator to make it a first-order operator. Geometers usually don't take the square root. So at any rate, if the spectrum of either one, the square root or just the Laplacian, is discrete. So if you label the eigenvalues of the Laplacian, okay, as the first eigenvalue, which is 0, this kills off constant functions, so 0 is an eigenvalue, and so on. Then you have the famous Weil law, which says that if you count the number of eigenvalues less than lambda, less or equal to lambda, count them with respect to multiplicity, you're going to get this constant times lambda to the n. So this is nothing but omega n is the volume of the unit ball. So this is 2 pi to the minus n times the volume of the manifold times the volume of the ball of radius lambda. Okay? So you get the right constant times lambda to the n, and then there's an error term. There has to be an error term because this is continuous and the spectrum is discrete. So the best you can say is that the error term is 1 lower order of magnitude. That's what occurs on the sphere. I'll talk about the sphere in just a second. And so this is a famous formula. So back in early 1900s, Lorentz was the most famous physicist. And he gave a famous lecture where he talked about how this formula should be true, but he said it just was not provable by the technology they had. Well, there was a young guy sitting in the audience named Weil, and he basically went home and solved it that night. And Hilbert also thought that it was impossible to prove this result. So Weil used the techniques of Hilbert and some new techniques. He put things together and prove this. So it's a very famous thing. It's sharp on the sphere, but in many other cases. In fact, generically, you can improve this error term. Does everybody know what this notation is? So big O means that you can control the difference between this and this by a fixed constant times this. Okay? Little o, as we'll see in a little bit, little o of something means that you can make it be smaller than any epsilon times the thing inside the parentheses if your lambda is large enough. Okay? So it's standard notation. And if you can see down here, I hope you can, the eigenfunctions are eigenfunctions of minus Laplacian. The eigenvalue for me, because I'm taking this as my operator, is lambda j. It's the frequency of the eigenfunction. And I'm always assuming that they're L2 normalized. Hope you guys can see this. And so if you do this, these guys, these L2 normalized eigenfunctions form an orthonormal basis for L2. Okay, sorry that's not so visible down there. Okay, so now let's focus on the sphere. I already told you a second ago that the Weil formula is sharp because the error term is of size lambda to the n minus 1 on the sphere. So on the sphere, the eigenfunctions are just the spherical harmonics. Spherical harmonics are the restriction of homogeneous harmonic polynomials of the Laplacian in Rn plus 1 to the n-dimensional sphere. They're called spherical harmonics. And you can calculate what the distinct eigenvalues are. They're basically k. And they repeat with a multiplicity that looks like the eigenvalue raised to the n minus 1. So for instance, when you're on the 2 sphere, this number dk is twice lambda. So there's exact formulas for this, and this is an exact formula for the eigenvalues on the sphere. So you can form eigenfunctions by doing something like this. This is called a coherent state. So what you do is you take the kernel, this part over here, you take the kernel for projecting onto spherical harmonics of degree k, okay, and you evaluate it at x and some point y naught. So if I didn't have this factor, this would be the kernel for projecting onto the space of spherical harmonics of degree k, and then I put this guy here to L2 normalize it. So these guys are just an orthonormal basis of spherical harmonics of degree k. So this is just, except for this factor, this is the kernel for the projection onto all spherical harmonics of degree k, and this is put there to L2 normalize it. Usually you have this point y naught being either the north or the south pole. Let's see if this works. Doesn't work. Oh, it doesn't work because I didn't do it correctly. Usually put y naught to be either the north or the south pole, and you can calculate, so usually y naught is up here, and you can calculate the size of this guy. There's classical formulas that go back to Sogge, for instance. You can calculate it, and you'll see that this is on the order of magnitude the distance between a point x and y naught, which is usually taken to be the north pole, okay, raised to this negative power. And the kernel is not singular, so you can cut off by putting this in there. So z lambda looks like the distance between either the north or the south pole plus 1 over lambda raised to this power. So it peaks at the 2 poles, the north pole and the south pole. So it looks like this, and the height of this peak will work out to be lambda to this power. Okay. So the size of this thing, which is the eigenfunction on the sphere, L2 normalized, the size looks like lambda to the n minus 1 over 2. It's achieved at the north and the south pole. Okay, and you can see that the LP norm of this function right here, okay, is the LP norm of the entire sphere is essentially achieved over a ball of radius 1 over lambda. So the LP norm over the entire sphere is essentially the LP norm inside little balls, shrinking balls of size lambda to the minus 1. Okay? And because of this formula, you can compute what the LP norm is. It's going to look like lambda to this power. Lambda to the power n times a half minus 1 over p minus a half. Okay? And this is a valid formula if p is bigger than this exponent. So it's just a simple calculation using very classical formulas about spherical harmonics to see that this particular function up here, which is called the zonal thing, this depends on the distance between x and y naught. This guy will have an LP norm that looks like this, and additionally, the LP mass on the entire sphere looks like the LP mass in a little ball about this point. Okay. So that's the story about eigenfunctions on the sphere. The ones that concentrate the most are these zonal functions. They really are peaking, like in this picture. They have most of their mass inside a little ball of radius 1 over lambda about the North Pole or the South Pole. Okay. So that's a pretty simple thing. There's another type of eigenfunction that has high concentration on the sphere. These are called the high Swage spherical harmonics. So the sphere is the unit sphere in Rn plus 1. So it's given by that formula up there, of course. And here's the formula for the high Swage spherical harmonics. You take x1 plus I, x2 raised to the kth power. This is obviously homogeneous. It's harmonic. In fact, it's homomorphic. And you put this to L2 normalize it. So the L2 norm is like 1. Okay? And remember, the distinct eigenvalues are given by this formula. So the spherical harmonic of degree k, if lambda and k are related like this, would be this. So if x3 up to xn plus 1 are the other variables, you could just compute the size of this just by putting absolute values. It'll be this times this. Of course, that's just high school mathematics. And then you Taylor expand this thing about 1, and you see that the size of this thing will look like this normalizing factor times this Gaussian. And these types of eigenfunctions are called Gaussian beams because they have this Gaussian type of concentration. So let me draw a picture of the size of this guy. So it's living on the sphere. Here's the sphere. Here's the equator. So the equator occurs when these variables are equal to 0. And the concentration will live in a tube about the equator, where the tube has width lambda to the minus 1/2. So these guys will have most of their LP mass in a tube about the equator, where the width of the tube is lambda to the minus 1/2. That's simply because this Gaussian will take over if this variable has size bigger than lambda to the minus 1/2, because of this times this. Okay? So these guys are very concentrated in a tube about the equator, where the width of the tube is like this. Okay? This is the equator. And the LP mass, sort of like in the case of the previous slide, the LP mass over the entire sphere will be almost exactly achieved on this very thin tube about the equator. And you could work out that, well, these are called Gaussian beams. They're practically 0, the places where this exponent is not close to 0. So if you're away from this tube, they'll practically be 0. So the size, this guy will look like this normalizing factor times the indicator function of this tube. If that were literally a tube, then the LP versus the L2 norm would be the volume of the tube, which is this with the minus side, raised to the 1 over 2, compared to the same thing with 1 over p. So the LP norm will have to look like this, because the volume of the tube is lambda to the minus and minus 1 over 2. Okay, so this is an even easier calculation than the previous slide. It literally follows from this. So once again, this is kind of similar to what happened before. This particular eigenfunction is concentrated near the equator. The equator on the sphere is a periodic geodesic. The sphere is unique because it has tons and tons of periodic geodesics. They're just the great circles. So given any great circle, you can find an eigenfunction that looks like this. It's going to be practically 0 outside of a lambda to the minus 1/2 tube about the great circle, okay? And it'll have those properties. Okay, better use this. Okay, and so it's the latter that's actually more interesting from the point of view of harmonic analysis. So you're capturing the L2 norm, or any LP norm, essentially if you take it over lambda to the minus 1/2 neighborhood of the geodesic. So in the case of the sphere, this would just be part of the equator. and this width is lambda to the minus 1/2, if you can read that. So this denotes the lambda to the minus 1/2 norm about unit geodesic. Okay? So these high Swage spherical harmonics have the property that they have quite a bit of L2 mass, basically 1, in a very shrinking tube about specific geodesics, periodic ones. Okay? And so it turns out that this is kind of typical. This is a picture of spherical harmonics, just take it from Wikipedia. So the center ones are the zonal functions. They're highly concentrated near the poles, okay? And depending on whether they're even or odd, they can be 0 or not 0 on the equator. And then these are the high Swage spherical harmonics. They become very, very concentrated about the the equators. So this is just spherical harmonics of degree 3. But if you went down, then very quickly these guys would just collapse. They'd be shrinking. They'd be practically, they'd be concentrated in very, very thin neighborhoods of the equators. Okay? All right, so it turns out that what's going on in the sphere is the worst possible case. And indeed, you can compute LP norms. Well, on the sphere, you're going to, from the previous slides, you had those 2 powers of lambda. So you had, where was it? You had this power of lambda, if you can see it, okay, for the LP norms of these high Swage spherical harmonics. And you had this power of lambda for the LP norms of the zonal functions, okay? And so the maximum of those LP norms, so the LP norm of the high Swage spherical harmonic versus the LP norm of the zonal functions will be lambda to the power mu, where mu is just the maximum of those 2 powers. So this is the power that detects concentration like Q lambda has, concentration around geodesics. This is the power that detects concentration near points. And it turns out that these 2 powers tie when P is this number. This is a number that pops up a lot, like in Strickhart's estimates. So when the dimension is 2, this is 6. When the dimension is 3, this is 4, and so on. So these guys, this guy has a larger LP norm if P is below or equal to this number, while this has a larger LP norm if P is above this number. Okay, and that kind of makes sense, right? So if you want to detect concentration on small sets, you're going to use LP norms with P large. Whereas if you want to detect concentration on bigger sets, you're going to use LP norms where the exponent P is small. And the zonal functions have concentration on the smallest possible set, points, while the high Swage spherical harmonics have concentration on a bigger set, equators. And they exactly tie. The LP norm of this guy is the same order of magnitude as the LP norm of this guy when P is its critical index, in which case these 2 powers are the same, just 1 over P. Okay? And so I proved in my thesis that this is the worst you can get on the sphere. So any spherical harmonic will have an LP norm which is growing like that. Okay? And I cared about it because I was interested in doing harmonic analysis on the sphere. That's what my thesis was about. And the thing that was good for me was that this exponent right here, if you know harmonic analysis, is what's called the critical index for Wagner-Ries summation. So if you can prove these LP estimates, then it turns out that you can prove sharp theorems about Wagner-Ries on the sphere, actually when you're above this exponent. And then, naturally, since I did this for my thesis on the sphere, I wanted to do it on a compact manifold. Way back then, in the mid-'80s, my main goal was to extend some things in harmonic analysis on Euclidean space to Riemannian manifolds. And the main tool, indeed, was to prove these sorts of estimates, that what happens on the sphere is the worst case. So the LP norms on a compact manifold grow no worse than lambda to this power. Okay? And I cared about it because of the application. This is the critical index for Wagner-Ries summation, and it's for this range. And so for this range, armed with this estimate, I could prove sharp theorems about Wagner-Ries, okay, when P is bigger than PC. And even the easy case of p equals infinity was not known, actually. So Michael Taylor and Hormander worked on that, but they didn't exactly have the right estimates, even though the suit norm estimates were known. But at any rate, that's a different story. So this is the estimate for eigenfunctions, and you could do a little bit better. So if you take the operator which projects onto a unit band of the spectrum, so eigenvalues between lambda and lambda plus 1, this denotes the projection of f onto the eigenspace with eigenvalue lambda. So this is projecting onto the unit band of the spectrum. So if lambda j were in this range, and f were an eigenfunction, then this would just be a formula for this. So a stronger estimate says that if you take the projection not just to a single eigenvalue, but to a band of the spectrum, you have the same sort of bounds. So it's actually, I lied a second ago. To prove the results, the applications to harmonic analysis, you need these estimates, slightly stronger estimates than this for projecting onto a unit band of the spectrum. Okay? So those were the estimates that had applications. Okay? All right, so let me quickly tell you how you prove this theorem that I hope that you can read. So it says that if you project onto a unit band of the spectrum, then the operator going from L2 to LP has a norm which is going like this. Okay, there's really three things that you need to know. So if you want to prove that theorem, okay, you interpolate between the trivial L2 estimates. It's a projection operator, so its norm L2 to L2 norm is 1. The L infinity estimates, I wish I could lift this up. So the L infinity estimates are saying that chi lambda of f is bounded from L2 to L infinity with this norm, okay? And then the other estimate is what happens for that critical exponent, okay? Oh, this is what I forgot to put. That's the size of the zonal thing. So PC is this critical exponent. So if you interpolate between the trivial L2 estimate, this L infinity estimate, which was known before my work, and this new estimate here, okay, you get everything. And I didn't know when I wrote the paper, I just fluttered a little bit. Everything actually follows from here. So this estimate follows from this estimate in a Bernstein inequality. So if you can prove this estimate, you get everything. Okay? Okay, so quite a bit of us over the last 15, 20 years have been actually trying to beat these estimates. Okay? Well, if you're just worrying about proving estimates for the projecting onto a unit band, it turns out in CDC you never can improve it, not on any manifold. And that's because this operator chi lambda, so the goal is to somehow improve the estimates on this page. You might have a chance of improving this estimate for individual eigenfunctions, but you can't improve the stronger estimates for functions which have spectrum lying in unit intervals. Okay, let me explain why briefly. So you can't improve when you project onto unit bands, and that's because, as you'll see in a second, when you prove these things, okay, you're using information about the wave equation. And these chi lambda operators are very local. They really only depend on information about the wave operator for a unit slice of time. So somehow, the linkage between singularities of the solutions of the wave equation and the dynamics of geodesic flow will be irrelevant. So if you want to detect interesting geometry, you're going to have to understand the behavior of the wave equation for a long period of time. Okay? It's just like if you watch a movie for a short period of time, you can't tell if it's a good movie or a bad movie. So if you want to detect interesting geometry, you're going to need information about the wave equation and hence the geodesic flow for a long period of time. These chi lambda operators are only based on unit pieces of time. Okay? So on the other hand, if you want to improve the eigenfunction estimates, well, Zeldich and I, the unique paper we wrote when he was at Johns Hopkins, showed that for a generic manifold, it doesn't work for the sphere, but for a generic manifold, you can beat the estimates provided that you're larger than the critical exponent. This is really about improving the suit norm estimates. So if you can improve the soup norm estimates and you use that interpolation argument that I said, then you can improve all the estimates when P is strictly bigger than PC. And then in a much more recent paper, Steve and I showed that in the real analytic case, you can characterize exactly when you cannot do this. So if you cannot do this and you're in the real analytic case, the manifold really has to look like a sphere. There has to be a point through which the geodesic flow is periodic, just like it is for the sphere. You pick any point on the sphere, then there's going to be a big family of great circles that pass through it. So any geodesic passing through that point will have to be periodic. It'll be a great circle. So we showed that if you can't do this, and you're in the real analytic case, then there has to be such a focal point. Okay? And these are variations on an old but famous result of Deutsch-Tremont-Gilliman, which is about when you can improve the error term in the Weil law from the first slide. You can also do that generically. So this is sort of a pointwise version of that. Okay? All right, so now let me turn to the main theorem I want to talk about, which is I'm going to characterize when you can and cannot improve the LP estimate. As I said, this is something that a lot of us have been worrying about for a while. So there's two cases. So you can say a lot if you're not at this critical exponent. PC is this number, if you have good eyes, 2 times n plus 1 over n minus 1. So if you're above it, then functions that look like zonal functions are relevant. If you're below it, then functions that look like the highest weight spherical harmonics are relevant. And so the theorem says that. So it says that you can improve the LP norms for P larger than PC exactly when you don't have lots of LP mass inside of teeny tiny balls of radius 1 over lambda. Okay? And you can also characterize when these two things are true in terms of L2 norms. So you will have improved LP estimates global LP estimates if you have improved local LP estimates involving balls of this teeny tiny size, same order of magnitude. And then there's an L2 condition, which says you can do these two red things if and only if the mass inside of balls of radius 1 over lambda, so that's the frequency, or 1 over the frequency, the wavelength, is little o lambda to the minus a half. Let me just point out that obviously this implies this, because this is a condition about the LP norm over the entire manifold. This is the LP norm over a subset. So if this is small compared to this, then the LP norm over any subset will be small compared to the same thing. And this follows from Holder's inequality. So if you do Holder's inequality, because P is bigger than 2, you can control the L2 norm by an LP norm. So by Holder's inequality, this blue thing is implied by this. So if you want to prove the theorem, the hard thing is to show that this third condition implies the first condition. So 1 is trivially implies 2, and by Holder's inequality, 2 implies 3. Okay, so this theorem is telling you that you can improve the LP estimates for large P if and only if the functions don't look like the zonal functions that we went over before. And then there's a corresponding theorem for small exponents. Those are when P is smaller than PC. Okay? So it'll say that you have relatively small LP norms. I showed before that the LP norm on any manifold is big O of lambda to that power. So you can get an improvement if and only if you don't have much, if and only if the LP mass on these shrinking tubes is the same order of magnitude. So as before, this implies this trivially. And then the other condition, which you probably can't see, is, let me write in yellow. This third condition is that if you take the L2 norm in any lambda to the minus 1/2 tube about a geodesic, then this is supposed to be small. Now the L2 norm over the entire manifold is 1, so this doesn't seem to be asking much. This is saying, you're saying, take a teeny tiny tube about a unit geodesic, so the tube has width lambda to the minus 1/2, the center is the geodesic, then you're requiring just that the L2 mass in the shrinking tubes gets small. So if that L2 condition holds, then this happens. So as before, by Holder's inequality, this red thing implies the blue thing, okay? And so the hard part of the theorem is to show that if you have small L2 mass in shrinking tubes, okay, then you have small LP norms globally. Okay? So, let me make sure I don't get behind. Okay, so that's a complete story, and I'm happy about that. It's, you know, it summarizes things we've been working on for a while. It's a complete story for everything except the critical exponent. It's hard to prove a corresponding theorem for the critical exponent because the critical exponent sees both types of concentration. Remember, for the critical exponent, the zonal functions, which are concentrating near points, have the same sort of LP norm for the critical exponent as the highest way spherical harmonics. So the critical exponent will detect concentration at points and concentration near periodic geodesics. So it's hard to get improved estimates for the critical exponent because if you try to do so, your proof will have to take into account both things. So it's harder. And so we don't know that there's generic improvement for those LP norms if you're below or at the critical exponent. My 2002 paper with Steve Zeldin showed that if you're above PC, generically you do get improvements. So we're not happy that we don't know generically that happens for this range or for the endpoint. If it happened for the endpoint, it would happen for everything by that interpolation argument from the beginning of my talk. Okay? Because of this. And so the previous slide shows necessary and sufficient conditions for getting improvement for LP norms for everything except for the critical index, but we don't know how to get necessary and sufficient conditions for improvement at the critical index. So there's some gaps and we know. On the other hand, we can prove some things. We can show that if those two necessary conditions, L2 mass in 1/λ balls is small, L2 mass in these lambda to the -1/2 tubes about geodesics is small, those are necessary to get improvement. So if we know those two conditions are valid, and if we also know that the manifold has no conjugate points, so for instance if it has negative curvature, then we can get improvement. And proving that theorem, that if you have negative curvature you get improvement for the critical exponent, is something that I've been interested in for a long time. I hate to tell you how long. The first time I met Peter Sardak, who was interested in these things too, we talked about this problem. So it's only recently that we've been able to prove these types of results. And actually, another thing I've been interested in for a long time, you can't read it, is that if the manifold has non-positive curvature, so negative curvature, or flat, getting log improvements, okay, beating these LP estimates by logs. So there's a very old result of Beyrard from the 1970s which says that if your manifold has non-positive curvature, you can beat the pseudonorm estimates by logs, powers of logs, but doing that for other exponents has only been obtained recently. Okay, so quickly I want to give you some sort of idea about how to prove these things, okay? So if you try to prove eigenfunction estimates on any manifold besides the sphere and the torus, and even there really, it's very difficult. You can't write down formulas. So in the first couple slides, I wrote down exact formulas for the worst eigenfunction on the sphere. They're very simple. But you can't do that on a general manifold. The formulas just don't work. So if you want to estimate eigenfunctions, you have to do it indirectly. You have to do it in terms of the mapping properties of an operator that reproduces eigenfunctions. And so here's the operator that you're going to use. You choose a nice bump function rho, say Schwarz class 1. This is the key condition so that it will reproduce eigenfunctions. You want rho of 0 to be 1. And then in order to bring the wave equation in, you want that the Fourier transform lives inside of the unit interval. Then you take these Fourier multipliers. It's defined by the spectral theorem. So rho of lambda minus p, p is the square root of Laplacian, will reproduce the eigenfunction because of this. So if you want to define this operator, acting on a function f, it's defined by the spectral theorem. You take the sum of the projection of f onto the jth eigenspace, and then you multiply by this. So if this has eigenvalue lambda j, so this guy acting on it will just be this number times Ej of f. So this is defined in this way by the spectral theorem. And so if f is an eigenfunction with eigenvalue lambda, then the term will only involve one term, okay? It'll involve E lambda and then rho of 0. So this operator reproduces eigenfunctions. And if you, in addition to this assumption, you also make this technical assumption that rho hat vanishes near 0, trust me, you can compute the kernel. So the kernel of this operator will be this power of lambda, which we've seen a few times before, like in the suit norm estimate, times a reasonable oscillatory thing. So there'll be a harmless amplitude, which is smooth and has bounded derivatives, and this oscillatory factor, which will look like e to the plus or minus I lambda times the distance between x and y. So if you buy this, then you can prove estimates pretty easily. So this is telling me that this is the kernel, rho of lambda minus p of f, that's a rho, not an f, will be equal to this guy integrated against f. So free of charge, you can get the suit norm estimates, because this kernel has this size, and so if I integrate this kernel against f, I'll actually get an operator going from L1 to L infinity with the size of the kernel, which is like this. And so by Schwarz's inequality, I get an operator from L2 to L infinity with a norm which is going like this. So if you buy this formula, this estimate is absolutely trivial. And it's not trivial to prove the LP estimates, but lucky for me, I could use oscillatory integral estimates. So these are called oscillatory integrals because when you integrate a function against its kernel, this is oscillating a lot. And these are studied in harmonic analysis quite a bit. So in the two-dimensional case in the 1970s, Hormander proved sharp results for oscillatory integrals of kernels like this. And lucky for me, when I was a graduate student in the 1980s, my advisor Stein proved sharp estimates in higher dimensions. He proved this in a paper that appears in what's called the Beijing Lectures in Harmonic Analysis. He was on sabbatical one year. He spent quite a bit of time away, including going to Beijing. So lucky for me, he did exactly the right theorem to be able to use this formula and use these two oscillatory integral theorems to prove this bound. Okay? So it was somewhat new technology, but this was kind of implicit in the work of Hormander and so on, that this is the right game that you would want to prove. So if you set up this game and you just use size estimates or use these classical now oscillatory integral estimates of Hormander and Stein, you get this theorem. And as I told you, this result can never be improved on any manifold. And I better write this formula so you can see it. I'll tell you why. So you can write this thing just using Fourier's inversion formula. Let me try to write it here. If I write it in white, maybe you can see it. So rho of lambda minus p, you think of p as being a number, and so it's 1 over 2 pi, and then the integral of e to the I t lambda, e to the minus I t p, and then rho hat of t. So this is the half wave operator. If I had cosine of Tp, it would just be the solution of the wave equation. Wave operator applied to u equals 0. U at the beginning of time is my initial data, and the velocity at the beginning of time is 0. So this is called a half wave operator. And so its properties for small time are very well known. They go back to Lax and Hormander. And so the problem is, if I'm doing this, because rho is assumed to only live in the unit interval rho hat, I'm only using information about this for unit pieces of time. As I told you before, I can't only watch the movie for a unit piece of time and just detect interesting geometries like negative curvature. Okay, but you can hope to sort of modify this, where you dilate your function rho like that, and then if you use properties of the Fourier transform of dilation, you get this formula. So you might expect to use this formula. This will also reproduce the eigenfunctions, because if I dilate rho, I'll still have rho of the dilation equal at 0 be 1. So they'll still reproduce eigenfunctions. And so you might hope to get a gain, because if you take T large, you'll be interested in the properties of this wave operator up to time capital T. So if capital T is large, you're detecting properties of the geodesic flow for a large period of time, so you might have a better hope. And you might also get a gain, if you play that game, from this factor 1 over capital T there. You won't get a gain on the sphere, because on the sphere, this operator is periodic. So on the sphere, what you're doing here is you're just taking an average of a periodic operator, so you can't get any gain. If you're not on the sphere, then maybe you will get a gain by playing this game. And there's a chance that it could work, because this is the properties of this for large times are related to the geodesic flow, the properties of the geodesic flow for large times. Okay, so maybe the strategy will work. Okay, if you play this game of kind of dilating the operators. Okay, and I'll go through this quickly, because this is easy. You could do this using other methods. So remember the first theorem. Oops, here it is. For large exponents, you get improved LP norms over the entire manifold. If you get improved LP estimates over shrinking balls, this is trivial. And by Holder's inequality, this condition is equivalent to the condition that you don't have relatively much L2 mass in teeny tiny balls of radius 1 over lambda. So the hard part of the theorem is to show that this bottom blue thing implies the top red thing. So let me very quickly tell you how to do that. And you could do this using elliptic regularity techniques. So you pick up Gilbert and Treutiger, and you look up lemma something point something, and it'll show you that this blue thing implies this red thing. Okay? But let's do it using the wave equation. Okay? All right, so the hard part of the theorem, the first theorem, says that having this small L2 mass in these shrinking balls gives you the small LP norms. Okay, so these guys reproduce eigenfunctions like we said. If you take T bizarrely enough to be 1 over lambda, earlier I was telling you should take T be large, but it turns out for large exponents, you take T to just be the radius of this ball. So if you take T to be this, then you can calculate this kernel. So using Huygens principle, it'll vanish when the distance between x and y is larger than 1 over lambda. And it's very easy to see, using trivial properties of the wave equation, that this kernel will have this size. So that's telling you that E lambda is literally just integration against this kernel. This kernel has this support properties and this size. So if you just use Cauchy-Schwarz's inequality, you'll see that E lambda at any point is controlled by 1 over the volume of this ball times this. So lambda to the n over 2 times the L2 mass inside of a ball of radius 1 over lambda about x. So if you just use this and you soup over x, you'll see that the soup norm over the entire manifold is controlled by lambda to the power for infinity, which is n minus 1 over 2. So you got lambda to the n over 2, so you have to distribute one of those over here. So you have lambda to the n minus 1 over 2 times lambda to the 1/2, and then the soup of L2 mass in any of these balls. Okay, so this fact right here just follows from these very easy things. And then if you just use my old estimate, okay, which says that that you have the LP norms over the entire manifold for P equals the critical power being bounded by lambda to the correct power, and use Holder's inequality, you get this. So if you interpolate use Holder's inequality, and you use the information about the LPC norms over the entire manifold in this thing, you'll get this. So you'll see that for any P bigger than PC, the LP norm over the entire manifold is controlled by the correct power of lambda. The L2 mass over the entire manifold raised to some exponent 1 minus theta. This factor is just 1. And then this factor, you could hope to get a gain. You're sipping the L2 mass inside of a 1 over lambda ball times this raised to some positive power. Okay, and you can't see it back there, but there's some classical results that the classical results of Beyrard, for instance, will tell you that if you have negative curvature, this will just be like a negative power of log. So using classical results, you know that this is small, and hence this is small compared to this. So if you have negative curvature, and generically by my work with Steve Zeldich, this factor will also have to be small. So this is fairly boring. So you can just use wave equation techniques or literally elliptic regularity to prove the theorem for P bigger than PC. And the interesting one, which uses harmonic analysis, is the other one. So the other one, I had three conditions. You get small LP norms of the entire manifold for P smaller than PC. If you have small LP mass in shrinking tubes, or if you have small L2 mass in shrinking tubes. So the hard part of the theorem is to show that if you have small L2 mass inside of shrinking tubes, you get small LP norms over the entire manifold. And so I call these Kakeya-Nikodym norms, because of harmonic analysis terminology. I say the Kakeya-Nikodym norm is just a soup over all these L2 masses over tubes. So I want to show that if these Kakeya-Nikodym norms, which are the soups over all these sorts of tubes, are small, then you get small LP norms. And so it turns out you can prove an inequality kind of like the last slide, where over here you have the correct power of lambda. Here you have the L2 norm of the entire manifold raised to some exponent. And here you have the biggest possible L2 norms over these shrinking tubes raised to a positive power. So this is a hard inequality to prove. So I proved this back in 2011, and I proved it following some early results of Bourgain. So this is one of the 2 or so times in my career where I could beat Bourgain. So Bourgain proved an estimate like this in 2D where he lost a little bit. He proved a weaker version of this where in particular he had to put an F plus epsilon for the power. And having a plus epsilon for the power is kiss of death. Because on using current technology on a manifold of negative curvature, you can only hope to get log improvements of things. So if you have to beat lambda to the epsilon powers, forget it, you're sunk. So getting rid of the epsilon loss was very important. And so I did this. So Bourgain's argument was using geometric ideas to go back to Cordoba and Pfefferman in 2D. And as part of what he got cited for the field medal, Bourgain developed this two-dimensional techniques from the 70s to higher dimensions. So Bourgain just used these geometric ideas, that's what he liked, and there was another way of obtaining sharp oscillatory integral estimates that I told you about before, which are due to Hormander. So there's 2 competing ways of proving sharp oscillatory integral estimates, the geometric approach of Cordoba and Pfefferman, and then the bilinear approach of Hormander. So what I did was I just spliced the 2 things together, and so I can beat Bourgain a little bit in 2D. And then in modern harmonic analysis, there's actually been quite a bit of work of generalizing these 1970s technologies to higher dimensions. Okay? And thereby people like Bourgain and Tao and Vargas and Lee and so on, Goose, Bourgain and Goose. So using the higher dimensional harmonic techniques, analysis techniques, in 2015, Blair and I proved this sort of thing in the much harder case of higher dimensions. Okay? So since I'm running out of time, let me quickly tell you how, if you have a manifold of negative curvature, you can make this be small. You can't if you're on the sphere. If you're on the sphere, then if you take the highest spherical harmonics and you take this to be the appropriate tube about the equator, this will have size 1, comparable to 1. So you can't beat the estimate. You can't make the L2 mass on shrinking tubes be small on the sphere, but you might hope to. And in fact, you can if you have negative curvature. So the results from the previous slide were from 2011. I like proving it, but I really wanted to show, remember, because of one of my favorite problems over the last 20 years or so, I really wanted to show that if you have negative curvature, you can beat things in this hard case where you're dealing with small exponents. Well, I did this, first of all, in the 2-dimensional case in a work with Steve Zeldich, and then it was generalized in higher dimensions. What we did was Steve and I showed that the L2 mass over the shrinking tubes is small, so little o of 1. And then Blair and I generalized that to higher dimensions in 2015. And then in 2016, we finally showed that the L2 mass in these tubes of radius lambda to the -1/2 is going to 0 like a power of log, negative power of log. Okay? And so if you use the thing on the previous slide together with the L2 mass being like a negative power of log, you finally get log improvements of these LP estimates. This is something I told you I've been worrying about for more than 20 years. And this is a natural result. It's the analog of what's implicit in this old work of Bayrard from the 1970s about getting log improvements for L infinity norms. Okay, and I won't go over this because I'm out of time and you can't read it. But so of the things I'm talking about, this is a hard estimate. It requires quite a bit of harmonic analysis. And showing that the L2 mass inside of these shrinking tubes is going to zero like log is also a hard result. Okay, so these are the two hard things in my talk. And this is another thing that fortunately I'm out of time, so I'll have to rush through, but I'll just tell you the story. If you're on a manifold of negative curvature, then you can use something that's like the Poisson summation formula. There's a universal cover. So in the case of the torus, the universal cover would just be Rx with the flat metric. So as you know, you can identify the torus with a cube, right? And so then you can translate the cube. If you periodic functions on the torus, smooth functions on the torus are in one-to-one correspondence with periodic functions in Rn. Well, there's a similar thing that happens if your manifold has negative, non-positive curvature. That's the theorem of Hadamard in 2D and Cartan in higher D. So when the smoke clears, there's something that's analogous to the Poisson summation formula, which is about Fourier series. And here's what it is. So remember down there, you're going to have to understand this operator on your manifold. You can write this operator, which involves the wave operator, in terms of the corresponding operator on your manifold involving the wave operator on the universal cover of your manifold involving the solution of the wave equation up there. So it involves summing over what are called deck transformations. In the case of the torus, this would just be corresponding to summing over elements of Vn. This would just be translating Y by such a guy. So you can identify the wave kernel on the manifold with the wave kernel on the universal covers by this formula. If you haven't seen it, don't worry about it. And you can hope to use information about the wave equation on the universal cover. So if your manifold has non-positive curvature, then the universal cover will as well. And so it turns out that if you have negative curvature, you have better dispersive properties for the wave equation on a manifold of negative curvature than you do on Euclidean space. So this operator is quite well behaved. So you can hope to estimate this guy pointwise, but what's going to hurt you is the number of terms in this sum will actually grow exponentially in capital T. So somehow you have to compensate the better properties of this with the fact that the number of terms is growing exponential in this parameter capital T. And so you do that by using microlocal analysis and actually using some facts from Riemannian geometry, but I'll skip that. And so if you use the fact that this and this are the same, you use this thing is like the Poisson summation formula, relating this and this. So you use something like the Poisson summation formula and some microlocal analysis, you can show that the L2 norms inside of the shrinking tubes are small, and hence this is small. And then, okay, I really will stop. You finally can get the improvements that I've always wanted to do for a long time for the critical exponent by using some other fairly recent harmonic analysis technique. So there's a result of Bach and Seeger that I've known about for a while. Put that I wanted to use this result in National Science Foundation proposals for a while, and finally got to use it. So if you have this estimate, then it implies by Chebyshev's inequality this estimate. This is called a weak type estimate. This is weaker than this. So Bach and Seeger proved a result saying that if you have this weaker estimate, it implies this estimate. So if you want to apply this theorem, you just have to apply this result down here, which follows, weaker follows from Chebyshev. And then there's another amazing result of Bourgain, which says that you can prove this sort of estimate. He just did this in a Euclidean case, but I realized you can generalize it if you have two types of things. You have a pointwise estimate for the kernel, and you have these L2 estimates, which I knew how to do from my work on nodal sets. So this is a result that's fairly easy. And this result, the fact that you have this estimate, is actually implicit in this 1970s papers of Bayrard. So if you use the result of Bach-and-Steger from harmonic analysis, and you use a beautiful argument of Bourgain, one of his most famous papers, you see that you just need these two estimates, which were already basically known, to get that. So I was very happy when finally could prove that. And I run over time, sorry about that, so I'll stop here.
Any question? 有人问问题吗？ It seems very get to me, don't understand that once you have a log improvement, how you get this improvement 1/t from?
Well, you beat the estimate. So instead of having eigenfunctions are controlled by lambda to a certain power, you have lambda to a certain power divided by a power of log. You don't improve the LP norms by powers. You can on the torus. The torus is special. In fact, there's recent, very famous and important results, decoupling results of Bourgain and Demeter that give very non-trivial improvements on the torus where you beat it by powers. So torus is quite special. So on a manifold of negative curvature, even if you assume the curvature is constant, like quotients of hyperbolic space, unfortunately the techniques are just getting log improvements. It's related to something in quantum mechanics called the Ehrenfest time. So you have to understand these guys. So you have a formula for what the main term of these guys should look like, but there's remainder terms. And the remainder terms grow exponentially. So you're gonna if you take log, so the exponential growth of the error terms is what forces you to only get logarithmic gains in the estimates.
还有其他问题吗？ Okay, no.
Okay.
Thanks.
Thanks.
Very good.